So just like the last section, section 12.2 with arithmetic sequences, we also have another type that we want to explore in this section called geometric sequences and series. So we're going to talk about the sequence, how we find a geometric sequence, finding the nth term, and then we're going to talk about geometric series, so summing all of these up. So with that, the definition for a geometric sequence, we define it recursively, which means we need to know the first term, and then we set up a relationship between the nth term and the one right before it. And so for geometric, if we do the division, so a sub n divided by a sub n minus 1 is equal to r. So they have a common ratio. So here's our definition of a geometric sequence defined recursively, where a sub 1 is a number and our ratio is not equal to 0. And it can be real numbers. So why don't we try some of these? First off, determine if the sequence is geometric. So in order to figure that out, I need to know what my first term is, which is 2. And then I need to find my common ratio. So if I did 6 over 2, or 18 over 6, or 54 over 18, or 162 out of 54, each time I do that division, I get a common ratio of 3. So I have my first term, which is 2. I have my ratio, which is 3. So this is geometric. The next one, show that the following sequence is geometric. So again, we need to find the first term. So that means we're going to plug in 1 here. We get 2 to the negative first, which is 1/2. Now we need to find r. To find r, we need to know what s sub n is and s sub n minus 1. So s sub n is 2 to the negative nth power. The one right before it is 2 to the negative n, I'm going to put parentheses here, minus 1. And just to expand that out, that's 2 to the negative n plus 1. So if we look back up top, we have to find the common ratio, it's a sub n divided by a sub n minus 1. Well, now we just have to divide these two. So r equals 2 to the negative n over 2 to the negative n plus 1. And if we remember our properties of exponents, we can separate that denominator, which is 2 to the negative n times 2 to the first. So these cancel, which leaves us with just our ratio of 1/2. So this shows that our common ratio is 1/2 no matter what term we have. We have our first term of 1/2. So this is also geometric. Last one on this page. Show that this sequence is geometric. In order to do that, we find the first term. So we plug in 1, which is 4. Now we need to find a sub n and a sub n minus 1, because this will get our common ratio out of this. So a sub n is 4 to the n. A to the n minus 1 is 4 to the n minus 1. And yes, this could be t to the n, t to the n minus 1. We're just doing the standard formula. So in order to find r, we do a sub n over a sub n minus 1, which is 4 to the n over 4 to the n minus 1. And if again we do the exact same process, we're left with just 4. So our ratio is 4. That means we have a first term, we have a common ratio. So this is a geometric sequence. Let's move on. We're going to be finding the nth term. So the next thing we want to do with geometric sequences is we want to find some term in that sequence. So in order to find the nth term, all we need is the first term and the common ratio. If we know that, we know a sub n equals a sub 1 times r to the n minus 1. This is our important formula that we want to use and utilize for finding an nth term. So let's try example 4. Find the nth term of the geometric sequence 10, 9, 81 over 10, 729 over 100. So what we need a sub 1, and a sub 1 is our first term, so that's just 10. Now, to find r, we could do 729 over 100 divided by 81 over 10, or 81 over 10 divided by 9, or 9 divided by 10. Either way, we're going to get our common ratio to be 9 over 10. So if I want to plug this into the formula to find the nth term, a sub n equals the first term times r to the n minus 1. That's the formula. So a sub n equals 10 times, what's our ratio? 9 over 10 to the n minus 1. So that's A. So for B, all we're asked to do is find the ninth term. So we want a sub 9. All we have to do is plug that into our formula. So that's 10 times 9 tenths to the 9 minus 1. So that is 10 times 9 tenths to the 8th power, which is approximately, if you type that into your calculator, we get 4.304. Last part, if I can save a little space. Find a recursive formula for this sequence. So if we flip back over to the front, this is the definition of a geometric sequence defined recursively. We need the first term, and we need to write a sub n in terms of a sub n minus 1. So our first term is 10. Then we could say a sub n equals our ratio, 9 tenths, times a sub n minus 1. That's all we need to define something recursively. So that's finding something with the nth term of geometric sequence. So once we do all that work with sequences, we want to go to sums of sequences or series. So let's just get a definition out of the way. The sum of the first n terms of a geometric sequence. So we're going to call that sum S sub n. And if we add up all of our pieces of the geometric sequence, we're going to write it out in our summation notation. So there's our summation notation, which is a sub 1 times r to the k minus 1. And if we work this out, it's going to be a sub 1 times 1 minus r to the n over 1 minus r. So this is the next important formula that we're going to be utilizing. Notice that r is not equal to 0 and r is not equal to 1. If our ratio was 1, and it wouldn't really make any change because all we're doing is getting a sum of an arithmetic sequence. So we're going to flip over and we're going to find some sums. All right, so on this page, we want to find the sum of the first n terms of the sequence 1/2 to the n. So that means we want to find the sum of 1/2 plus 1/4 plus 1/8 all the way up to 1/2 to the n. So here's our summation notation. So what we want to do here is we want to use the formula that we had on the previous page. So the formula that we want to use is S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. So in this formula, we need to know what a sub 1 is, and we need to know what r is. Well, luckily, our sum already gives it to us. A sub 1 is 1/2. That's this number right here. R is what's in the parentheses, so it's also 1/2. So if I want to find the summation of this, we just plug those two values in. So we have S sub n equals 1/2 times 1 minus 1/2 to the nth power all over 1 minus 1/2. Now if I do a little algebra, 1 minus 1/2 is 1/2. These two 1/2s cancel. So this sum is equal to 1 minus 1/2 to the nth power. All right. So a nice feature, really powerful features of sums is if we are talking about an infinite geometric series. So this is the notation that we use if n's going off to infinity. So here n's going off to infinity. Here's our sum, our first term, r to the k minus 1. If we do a little algebra with this, I can separate this fraction, if I distribute the a sub 1, to be a sub 1 over 1 minus r, that's a sub 1 times 1, minus a sub 1 times r to the n over this whole thing. So this really important topic in especially series, we want to talk about convergence. Convergence, we say a series converges if the finite sum, should say infinite sum, approaches some number as L, or some number L as n approaches infinity. That means as the n's get larger and larger, the number of terms gets larger and larger, we're getting closer and closer to this value L, which is a crazy idea that these sums, if we keep adding things up, gets closer and closer to a number. So if it doesn't converge, we call that a divergent series, which all that means is a series does not converge on a number. It's going in opposite ways. And here is the really, really powerful concept from here. If we have the absolute value of r is less than 1, the absolute value of our common ratio is less than 1, then the infinite geometric series converges, and all we need is this formula. So on the next page, we're going to be utilizing this formula to find out a bunch of different stuff. All right, so with example 7, determine if the geometric series converges or diverges. So we're going to utilize that formula that we had on the page right before. We need to know what a sub 1 is. A sub 1 in this case is this number right here, 2. It's always in our series. We need to know what our r is, which is the number inside this parentheses, 2 over 3. So if r is less than 1, so if absolute value of r is less than 1, then it has to converge. So we look, is our r less than 1? Yes, so it does converge. And what does the sum add up to? Well, our sum of this sequence is, let's write out the formula. Let's just say our sum is a sub 1 over 1 minus r. There's our formula. We know what a sub 1 is. That's 2. We know what r is, 1 minus 2/3. So this is just 2 over 1/3, which is 6. So no matter how many terms, the more and more terms that I add to this series, I'm getting closer and closer to the sum being 6. Last up, this is something that might have bugged some of you guys for a while, but why does, if you know that 3 over 3 is equal to 1, why does 1/3, which is equal to 0.333333 repeated? What if I did 1/3 plus 1/3 plus 1/3? That equals 1 fractionally, right? But what if I did 0.333333 repeated plus another one plus another one? Why is this sum? Why is this 1? Because that's 99999. So why does your calculator know that this 0.99999 is equal to 1? Well, it knows it because of this geometric sequence, this series. So let's just, if we wrote this out, this is this sum, which we want to come up with a summation of infinity starting at 1, is, well, let's write this out. It's 0.9 plus 0.09 plus 0.009 plus 0.0009. And it keeps going, right? So if I wrote that as a fraction, that's 9/10 plus 9/100 plus 9/1000 plus 9/10,000. So you see it keeps going and going and going. Our first term is 9/10. And how is it changing? It's changing by 1/10 each time. So that's 1/10 to the k minus 1. Here is our infinite series. If we have our infinite series, we can just jump to our formula that says the sum of all of those is a sub 1 over 1 minus r. Well, what's our first term? 9/10, and 1 minus 1/10, which gives us 9/10 divided by 9/10, which is exactly 1. So this statement of just adding up thirds, proved by geometric series, has to equal 1. So hopefully that's clarified some things for you guys. The homework, just like usual, is at the bottom of the page. We'll do some of these problems in class, and good luck.